Yeah, so I'm John Digos, and I'm going to talk to you about streams. Actually, I'm not. I lied. I just said I was going to talk to you about streams so I could get you in the room. What I'm actually going to talk to you about is functional programming. And sort of by the way, we're going to happen to use a stream to do some of that exploration of some concepts in FP. So today we're going to talk about induction and co-induction a bit, just to sort of frame this from a more theoretical background. And then we're going to talk about just how universally applicable streams are. You can actually use them to solve a ton of real-world problems that everyone in here is wrestling with on a daily basis. And then I'm going to introduce an abstraction in functional programming called CoFree, which you may or may not have heard of. Has anyone heard of the free monad? Go to Kelly's talk or anything? Yeah, so a fair number of people have heard of the free monad. The CoFree is the categorical dual of that and is super useful, or at least it's possible to model streams using CoFree comonads. So if those words scare you, don't worry, you're not alone. But we're going to go through them one step at a time and hopefully make a little sense of this. And then finally, I'm going to end with a little sort of call to arms and a challenge, and you'll get to see what that's about soon. So induction. Induction is the process of tearing down a structure to culminate in a terminal value. And there are tons and tons of programs out there that have the structure of an inductive program. For example, parsing a config file, or sorting a list, or even generating an HTTP response that you send back from a request, or computing the millionth digit or any other specific digit of the number pi. These are all examples of inductive programs. They start from some initial structure, and then they do this, 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 and then finally they culminate in a single value. However, it actually turns out that most business problems are not inductive. They're actually something called co-inductive. So what does that refer to? Well, fundamentally, co-induction is the process of starting from an initial value to build up an infinite structure. And you should view it in your mind as the opposite of induction. Induction is starting from a finite structure and sort of tearing it down to produce a single value. And then co-induction is the opposite process of starting with that value and building it up into this potentially infinite data structure. And there are tons and tons of examples of co-inductive processes. For example, producing the next state of the user interface given a user input. User does something, and that results in the next state of the user interface. Or producing the current state of a config file given an update to the config file. So that happens sometimes if you want your application to be live updatable, you want people to be able to configure it on the fly, then of course you're going to have to build a little co-inductive process around that. Also, I just used the example of generating an HTTP response as an example of an inductive program, but we can sort of zoom out and look at the big picture. A web server. A web server is co-inductive, right? Because you have this infinite stream of HTTP requests or whatever, and you're transforming those requests into responses. And finally, another example is producing the millionth of digit of pi is inductive, but producing all, or rather describing the process for producing all the digits of pi is an example of a co-inductive process. So programming languages, they really, really hate co-induction. And why is this? Well, every programming language is made up of functions and methods and stuff, and these things return single values. Even your main function returns a single value after doing a bunch of stuff. Most languages have no support for co-inductive concepts. Some, like Idris, actually have a notion of co-data and co-recursion. And some, like Haskell, sort of blur things so you can use it for both. But most programming languages don't have anything. Actually, has anyone heard of generators in JavaScript? Okay, yeah, so finally, after 40 years, they added a co-inductive construct to a programming language. Unfortunately, it's not very good and not very composable, so there's that. But at the same time, like, it's not escaped people's notice that the business problems we solve today are largely co-inductive in nature. And hence the rise of reactive and streams. In fact, I hear a whole company was built around the concept of reactivity. You may have heard of them, Lightband, formerly known as TypeSafe. So streams are really great, easy to understand examples of co-inductive processes. And you can find streams used in data processing, web servers, user interfaces, discrete functional reactive programming, and so much more. They're really all over the place. And a good chunk of you probably came to this expecting to learn about streams, so you must have some application in your mind for them. Well, so streams they give us a few capabilities that are really interesting and important for building programs. One of which is they're stateful. And I don't mean that in an impure way, like mutable state, because you don't need mutable state in order to model the concept of streams. I mean that in simply the state of a fold, for example, where you're passing in a state and returning a new state. You can model state in a purely functional way. And all streams, whether they're functional or not, they allow you to build stateful things, stateful machines. They're capable of doing incremental computation. And of course, that's why they can handle infinite processes like a web server that runs forever or a user interface that never shuts down, because they can do things little chunk at a time. Of course, they can be infinite in nature, and many streams are infinite, or at least they don't have a well-defined ending point, like the web server example. You can shut it down, but it could also run forever. And finally, they consume information and they also emit information. Sort of one step at a time, you can use them to build all sorts of interesting data processing pipelines. So when it comes to using streams, you have lots of choices. You do not suffer from a scarcity. You have obviously Akka Streams and Java Streams and scalaz-streams and the successor to that, which is FS2, and then lots of other stuff. And that's just sort of easily accessible from Scala. In the big data space, you have Spark and Flink and Pachyderm and Kafka and just on and on and on and on. There's so many libraries out there for stream processing. And a good question is, okay, say you have some little use case in mind. It might be small, one project, or it might be massive. It might be the next big thing that your company depends on. How are you going to choose between all of these different abstractions around the notion of streaming? I'd like to give you a little bit of help there in the form of a few laws of clean functional code. And let's go through these one at a time. I think you can use these principles to both help you choose libraries to solve problems that you have, but I also think you can use these principles when you're building your own code, especially if it's being used by other developers, or if it's open source and it's going to be read a lot by other developers. So first off, reasonability is directly proportional to totality and referential transparency. Meaning if all your functions are total, for some input, they'll always return some output. And they're referentially transparent, they're pure, they don't do side effects, they return actual values rather than just discarding information into the ether, then the ability to reason about that software goes way, way, way up. Because then you have that guarantee. If I send a value to a function, I'm always going to get back the same return value for the same input. So that affects testability, reasonability, composability. So many useful properties come out of that. Composability is inversely proportional to the number of data types. So I want you to look at libraries like that. When you see a library and you see 1,000 different data types, 1,000 different classes, I can guarantee you that library does not have good composability. They've built a bunch of monoliths that don't combine together in general purpose ways. And the reason for that is like composability, it wants to be like Lego building blocks where you have a small number of things and you can use those to snap them together in an infinite variety of way. Obfuscation. So obfuscation is directly proportional to number of lawless interfaces. And what I mean by that is when you create an interface and that interface has methods, and those methods, they don't have any laws, that means the sole information communicated by that interface is in your intuition about the name of those methods. And that's a way of obfuscating intent, right? Because what we would like to be able to do is create laws around our interfaces that give us generic reasoning principles that we can apply to all implementations of a given interface. And if you find you cannot express any laws over an interface, there's a good chance that it's because it doesn't have any, and therefore it's sort of ad hoc. It's going to be very, very hard to reason about that in the general case. Correctness is directly proportional to degree of polymorphism. So the more monomorphic your code is, if you have fixed definite types, there's lots of ways to implement every function. When things are polymorphic, you have fewer ways to implement every function, and the correctness tends to be much, much, much higher. Extremely polymorphic code, like has anyone taken a look at Lens? Especially like Ed Komet's Lens in Haskell, super polymorphic code. In many cases, there's only one way of writing these functions, and it's the correct way, sort of not coincidentally. Shoddiness. So what is shoddiness? We all do this, of course, and lots of libraries do this. And it happens when you create some really nasty, horrible thing that you never want another developer to see, and then you use encapsulation to hide that. Because if they see and play around with that, that's like tinkering with an atomic bomb or something. So the more encapsulation you see, like when the guts aren't exposed, there's some nasty stuff going on down there. And of course, sometimes we need to do that, right? We're programmers, we're paid to get stuff done. We need to do that occasionally, but it is always a sign of shoddiness. And finally, volume is inversely proportional to orthogonality. What I mean by that is you're going to have more code if you don't have those Lego building blocks. So if you're able to factor the problem space in such a way that every aspect is independent from every other aspect, then you're going to dramatically cut down on the total amount of code that you need in order to solve a given problem. So how do we apply these things to streams? I don't know. This is the classes inside of Akka.stream. And I don't want to trash talk Akka.stream, obviously. Great library, it's used to build bulletproof production systems. So, and many of us use it and have used it and will continue to use it. But I do want you to consider the following, that it behooves you in many cases to choose the least powerful abstraction for the job. Choose the most constrained one, because that's going to give you tremendous power on the flip side. And I don't have time to go into what that means, but there's an excellent talk by Runar on that, constraints liberate and liberties constrain, which I recommend everyone check out if you haven't already. Really excellent talk. Choose the smallest interface that gets the job done. And for some problems, I can guarantee you this is not it. And for other problems, it may be. But for some problems, this is definitely not it. So what can save us sort of from lots and lots of complexity? What if I told you there were an abstraction that gave us extremely high reasonability because it's absolutely 100% total and referentially transparent? Or that there's only one data type in the entire library. There are no other data types, it's just one. And you can use that one to combine together in lots of different ways. Or what if I said there are no lawless interfaces? Every single interface has well-defined laws that have been sort of well-studied and well-tested. And that it's super polymorphic. In fact, many implementations of functions, there's just a few. There's just a few to choose from, and usually one reasonable one, so it makes it much easier to get that code correct. You don't have to hide anything, and everything is totally orthogonal and composable in bits and pieces. If I told you all that, you'd probably laugh, right? There can't be such a thing. CoFree. CoFree is the abstraction that you've been looking for. It has all the power free, but with the ability to do streaming. For those of you who don't know what free monads are, think of them as a data structure that describes a sequential computation, where subsequent steps in the computation can depend on the result of previous steps. That's all a free monad is a description of a program in terms of a data structure, where the data structure models the different things that you want to do in that program, and where one of those instructions can depend on the result of preceding computations. And CoFree is the same way, but it's designed for co-inductive processes, so it has all the power free, but it's designed for the streaming stuff that we see on a daily basis when we're trying to solve real-world problems. This is what CoFree looks like, and it has a strange sort of definition if you look there. A CoFree of F, first F is a higher kind of type. So it's a type constructor of one type parameter. List, you could stuff in list here, or you can stuff in option, because both list and option accept one type parameter. And then this A is the type of the value stored inside the CoFree, which is called head. And the head contains an element of A. And then the tail, it contains another CoFree of f of A, but wrapped in an F. So let me give you two intuitions for what this thing is. Try to keep this in your mind as I'm explaining them. First, CoFree of f of A is a co-inductive process that generates A's using effect F. So the CoFree has the A, and then to get the next CoFree in there, you're going to have to execute the F, where F represents some sort of effect. It could be task or promise or future, for example, but it could be lots of other things. Another intuition for this that is useful in some cases is that a CoFree of f of A is a current position A on a landscape, infinite landscape, that requires effect F to move to a new position. So on this landscape, you can move to new positions, but they require you to execute Fs. And I really like this particular intuition for CoFree. It has everything, comonads or CoFree has the functor stuff, well, the functor method, which is map, and the functor laws that go along with it, because CoFree is a functor, forms a functor. It also has two other methods, one called extract, which basically tells you where you are at in the landscape of possibilities. And this, I call it terraforming method. I tried to think of something clever there, but that's the best I could do. Extend, which allows you to basically feed it a function that's going to produce a new B, and it's going to form a new landscape of Bs on top of that. So you can look up their laws if you like. And here's how we would use this CoFree data structure to model the Fibonacci sequence, which of course is infinite. There's just a few lines of code, and we can describe an infinite sequence of Fibonacci numbers using this. We just construct, we have to use this lazy type called name, which stands for by name. And this lazy type just ensures we don't eagerly evaluate the tail of the CoFree data structure, because then we'd run out of memory and blow the stack. So we defer that. We create a lazy structure by simply, for F, our choice of F in this case is going to be basically a thunk that defers evaluation of the thing that it produces. And so CoFree of name of A is actually a lazy sort of infinite list. And I use that in this case to model the Fibonacci sequence. All right, so what can we do with this? Well, one of the things that we can do with streams is we can append one stream to another. That makes sense, right? If the first stream is finite, then it makes sense to append something else to that stream. And it turns out you can implement append by requiring your F not only be a functor, but it be something called applicative plus. So applicative is a type of functor that's a little more powerful than an ordinary functor, and it has additional facilities, and plus allows you to take two of these applicative things and smash them together, basically combine them in a certain way. And once you have that capability, you can take two CoFree processes and you can append them, such that you're going to basically explore the one before you start exploring the other landscape. Also, to sort of prove that these things really are as powerful as like Scala collections and other types of things, it's very simple. You can write this method called collect, which can take any CoFree of f of A, and it can pump it. It can pump it for values. It can just keep on exploring and stuffing those things into a vector, and then end up returning that vector inside an F. And I won't go into the implementation, but you can explore that on your own and see how it works. And disperse is the inverse of that. So if we have some sort of sequence and we want to disperse it into a landscape, CoFree landscape, then we can call disperse, and it requires, again, F be applicative plus. So here, this should demonstrate, hey, we really can use these things to model things like Scala collections, right? And of course, we saw in the case of fibs that these things can be lazy and infinite. Here's zip. So you can actually take two CoFree structures and you can zip them together. There's a couple different ways you can do that, but this is the most common one. The only requirement is you have to be able to zip the F's together. So for something like name, that's trivial. For list, trivial. And most of the types of type constructors, one type argument that you can probably think of, like data structures and whatnot, zip is trivial. And so you can implement this zip with method quite easily. Fold. Why can't we fold over a CoFree structure?
Because it's potentially infinite.
Exactly. It's potentially infinite. So folding doesn't make sense. Folding doesn't make sense at all. But what we can do is the scan operation, which sort of produces every intermediate. And it never produces the final value. It just keeps on scanning, producing that building up of state. But this is the equivalent of fold. If you want to do something fold-like using CoFree, you use scan. And of course, Scala has scan left and scan right and so forth on its own collections. You can even filter these things. So that's pretty amazing. There's two ways you can filter. If you have a CoFree, you can zero out the elements that you don't want, but you can also actually remove them. And they require different degrees of power. So in the first one, if you just want to zero out the stuff you don't want, which could be useful if you're using like a byte vector as your F, because you have these streams of bytes, then you may just want to zero them out, and zeroing them out corresponds to empty byte vectors in chunks of data that you didn't want to process. However, the other way is to require that F be a monad, and when you have that much structure, you can implement filter such that actually deletes the slots that your predicate passed to filter doesn't want. Well, that's streams. Can we do something better? Can we do sources and sinks? And it turns out the answer is yes. And it's not that totally yet. Okay, so, well, that concludes my presentation on streams. However, I want to leave you with a final challenge, and that is go read the slides after the fact and look through the code and see everything that you can accomplish with a single data type and entirely lawful type classes. And then I challenge you to, in your own code, maybe you don't end up using CoFree for streams, but take one thing, and try to simplify your application by using something in functional programming. Thank you very much.
Thank you.